thanks, Lucian, for this great introduction, and thank you for mentioning that I'm a real coffee guy. They're actually making me do some real work on this board. There will be coffee in this talk, but I'm going to talk mostly about structured data in search results, okay, which is one of the what I would call probably the most interesting or new development in web search in the last few years. Now, the other talk I wanted to give is what I would title a decade at Google. Now, I'm looking at some of the faces here. A decade? Say 1 decade. Who are you joking with? At Google, a decade is a long time. If you spend a decade at Google, which I have not yet. I actually have 4 weeks until my 10-year anniversary. But that puts me in the top 2% of, in other words, 98% of the people joined after me, which is kind of scary. But some of the experiences from 10 years at Google will sort of come into the talk in various ways. And I should say, thank you for having me here. This is a beautiful space, and so nice to see so many good friends and
it used to be the library.
Now what happened?
We don't need it since Google.
Don't need a library.
Yeah.
Okay. So, so going back to the theme of 10 years at Google, about 5 years ago, this is the slide that I used to start my talks with. And the goal then was, remember, I came to Google, that I mentioned 10 years ago, where it was a very document-oriented company. Okay? All we did was we crawled documents, we indexed them, very IR-ish DNA, if you want, intellectual heritage. Okay? And the question was, and you know, that worked, right? I mean, there was a good ecosystem where people created content. The search engine was able to discover this content, and so there was more motivation for people to create the content, and the ecosystem worked. And the question was, how can we create the same ecosystems for structured data on the web? How can we make it easier for people to create structured data, for people to discover structured data, and to do the things with structured data that you cannot do, or that you don't need to do with documents, like query it, like integrate it, like visualize it, and stuff like that. So this was sort of the vision of what we were trying to create on my team and some of the other teams. And so we were working on a bunch of pieces of this. One was the creation of data. So we created this thing called Google Fusion Tables, which is still out there and still doing well. The idea of Fusion Tables was to make it easy for people to create or to take their structured data and do interesting stuff with it. Okay, visualize it, share it, sort of I like to call it a database system for the 99%. So we focused on several tasks that we made them very easy. Bring your data in, visualize it, put it on a map, maybe talk about it in a news story. This is one of my favorite use cases. Favorite is actually a bad word here. But this is was used in the crisis response after the Japan earthquake in 2011. Does anybody read Japanese here? Okay, I can say whatever I want. So this is either where there were shelters for people who were displaced after the earthquake, or where there are going to be electrical outages. But this map received something like 100 million views per day for about a week in the time where people really need the data. And you know, actually, the interesting story about this is this was created by the Google crisis response team, and they put it on the Google homepage in Japan, and it got a lot of traffic, but not that much. And then the people at Yahoo noticed it, and they put it on the front page of the Yahoo Japan, and then it started getting all the traffic. Because this is Japan. So this was on the side of the creation of structured data. We actually had a great example of data integration, one of my favorites ever. This is, again, after the Japan earthquake, somebody asked the question of where are there nuclear plants in earthquake-prone areas? Okay, so somebody did data integration. In this case, the integration itself was pretty easy because all you had to do was put both of them on a map and put it on a Fusion table. So the red zones are, so they took the data set with all the earthquake activity since 1973. So red means you shouldn't live there unless you really like to be shaken in the middle of the night. Green, or I guess the rest is okay places, and then the purple dots are where there are nuclear plants. And so now this visualization actually answered the question that a lot of people had at the time, which is, okay, are we in trouble or not? This is the power of data integration. These are two data sets that were not created thinking they would ever be integrated, but they were integrated on the map. We also worked on discovering data that was already there. So we started this project called Web Tables that I'm going to tell you about a lot today, which was, hey, there are a lot of people who already created good, high-quality data sitting in HTML tables somewhere out there on the web. Let's find them and let's do something interesting with them. But we were a little bit challenged with. So we found good data. We helped people create data, but the discovery aspect, when you came to the Google search engine and looked for data, how to find that data and therefore drive that whole ecosystem, that was where we were still challenged. So then came the knowledge graph. Okay, the Google Knowledge Graph, which I have nothing to do with. We bought a company called MetaWeb, which created Freebase. We're the only people who paid so much money for free base, which is now available freely for everybody else. And today, in a large fraction of search results, you actually get this thing is called the knowledge card. So now, and this is 4 or 5 years ago already, now we identify that there are entities in the world. Okay, for us database people who've been around the database community for more than a decade, this is a small, sort of an obvious step. So if the search engine recognizes queries about an entity, we have a database with entities and with properties of these entities, and we can now display these things. Okay, this was a major effort at Google and followed by other companies. Not only that, we can start looking at more complex queries. And complex, please, people, complex is not what you're thinking complex SQL. Okay, this is like Microsoft Award. So this is a property, a simple select statement of a property, a projection on an entity. Okay, so we understand that. We don't get into trouble. Okay, so if you ask something very controversial like Taylor Swift boyfriend, we're back to the 10 blue links. We're not going to try to venture into our probabilistic database to see whether candidates. Okay, so we do back off when we see trouble. We can do set-oriented queries. So now you're asking for Woody Allen movies, and so now we identify that there's a set of objects that is also represented in the knowledge graph, and so we can give you a nice visualization of the results. These are probably ranked in some popularity, some way. And then structured data can also be funny. So Stephen Colbert, this was about a year ago, maybe a year and a half ago, did a Google search on himself, and he discovered that the Google Knowledge Graph thought that he was only 5 feet 10. And he's like, no, I've been 5 feet 11 since the age of 14. I'm not 5 feet 10, you just took an inch away from me. Okay, that puts me in a completely different class of people. I actually read the article, it's hilarious. So he complained, he called Larry Page, and he complained, he said, maybe you're 5'11", I'm also 5'11". Okay, I want you to fix that. So this is how Google fixed it. This was actually a real screenshot. We heard this up for a while. So we fixed it, and okay, we gave him, we made sure that everybody knew that John Stewart is shorter, and life was good for a while. So you can see, so certain data can actually be, can get on people's nerves or make them laugh. So the Google Knowledge Graph is a huge database, okay, of facts. It's actually triples. Okay, that's the way we model them. There's a lot of, it's created using manual effort, meaning that we crawl a lot of data from various sources, but then there's there's quality assurance, meaning that the correctness has to be over 90-something%, and that varies a little bit. But data doesn't get in there unless there is enough statistical evidence that it is correct. Okay. There were efforts like the Knowledge Vault started a couple of years ago to do a probabilistic knowledge base that actually gathered information from multiple sources and suggested probabilities. It actually was surprising how little extra number of triples the Knowledge Vault found that were really high quality. So that's, and the reason is probably that they focused on the head queries or the head content, and that head is pretty well covered. The facts need to be objective truth. Okay, nobody's going to ask here how many nuclear weapons does Iran have. Okay, we're not getting into that. We don't want to. And the focus is on the head. Okay, this is a really important point. The focus here is on the head content, on head queries, and whenever we expand the knowledge graph, we look at the query stream, we say, okay, where is the weight of the queries that we can still serve, that we haven't served yet, and extend the knowledge graph. Okay, so this is a really important point. We also have another effort, which is where we get answers from the web itself. Okay, so if you ask, where was Fahrenheit born? Okay, we don't have that, maybe we do, but it's irrelevant. We don't have that in the knowledge graph, but we can find a sentence on the web coming from a very reliable source, meaning that source would have been ranked pretty high up, and the information extraction NLP techniques were pretty confident to give you this as a result. Okay? And this example is interesting because when I compared it with my neighbor who works for Apple, he asked Siri the same thing, and the answer was, what was it? It was Gdansk. Siri just came back saying Gdansk, which is correct. No problem with that. This answer is kind of more interesting because it actually, he actually was born in Gdansk, but spent most of his life in other places. And so this answer gives you a little bit of context, okay, which is kind of new for us database people, right? I mean, we're used to giving or tuples, but when people actually ask questions, they actually may want a little bit of context around it so they can actually get a more interesting answer. And this works sometimes, and sometimes it gets Google into a lot of trouble. Like, I think if you ask this, you can find the articles in search engine land that talk about, if you ask them, does Jesus love? We don't have a very politically correct answer for that. And we also have answers coming from real content, tables on the web. And this is the result of the web tables project that I'll tell you about in a moment. So there are efforts going into the knowledge graph, and there are efforts that are trying to find answers in the search results themselves, assuming they're high enough quality and can be lifted up to the top of the page. With that background, I'm going to talk about 3 projects today. One is the HTML table. So this was, if you want, I call it a long but successful flood. This started 7 years ago. I'll tell you how, I'll tell you some of the challenges. But today, if you go to google.com and you search for data that can be supported by HTML tables, in some cases you'll get an HTML table, and you can call me and congratulate the team that I helped create. Okay? The second project is, now that we're thinking about databases and entities and their properties, we really need to think about schema in a much broader way. Okay, today the schema of the knowledge graph is very much what data it has. But if you're going to have data, you might actually want to think about schema more broadly in terms of schema for stuff that you may not know about, but you should know the schema. Okay? And so Viperpedia is an effort that we started a few years ago that is starting to have real impact and is really taking a broader look at schema. And finally, we want to challenge the fact or the assumption of the knowledge graph, which is you only look at very objective truths, and say, well, a lot of answers, a lot of questions are actually asking about subjective facts, and some of them are subjectivity can come with a certain degree of confidence, and we actually mine subjective facts with high confidence from the web. And this is obviously a very exploratory project. So I'm sort of giving you a smorgasbord of products to research. And please ask me questions anytime. In particular, when I look at my cell phone, it's not because I'm answering calls, it's because I don't have a watch. So I'm trying to keep track of time. So these are web tables, okay? The nice thing about working at Google, in 2007, I was able to do a map reduce over the index and ask how many HTML tables were there on the web, or in the Google index. And the answer came back 2 hours later saying 14 billion. So all I did was we looked at table tabs inside HTML documents, counted how many there were, and put them in a corpus. And some of them are very useful, like football league coaches or probability of various events in poker. So, so the idea was, look, there's a lot of really good content here. I mean, even if you decrease this by a few orders of magnitude, which we had to later because the vast majority was not very good, you're still left with something like 150 million really good tables. Okay, that's, I don't know where else we can find 150 million tables. So the question is, can we find the good from the bad? Okay, can we find the needles in the haystack? And does anybody care? Can we bring them to applications in such a way that they actually make a difference to anyone? So this was started by an intern project in 2007. Half of the interns on the project are today professors at universities. So Mike Caffarella was the sort of the ringleader on the project. He's at Michigan. Daisy Wen was in Florida, and what's his name at Columbia? One of the Woos. Okay? And we launched a table search externally in 2012 after Kong Yu and a couple of colleagues came. Eugene Wu, sorry, Eugene Wu. Kong Yu came to Google in 2010, and then a year and a half later launched Table Search, which I'll tell you in a moment. And we reached the holy grail of Googleness in 2014, early 2014, when we launched tables as part of Google search results. Okay? So what is the strategy here? You go through the Google index, you look for things that look like tables, and yes, there's a lot of other content. There are lists, there are things that are sort of repeated structures that we started looking at, but in this case I'm focusing on tables, and then you start trying to find the good from the bad. Okay? And unfortunately, less than 1% of these HTML tables are actually what I would call good data. Okay? So this presents a real problem for machine learning. Because if you're going to try to use machine learning to classify the good from the bad, well, if you just always say no, you're going to be 99% precise, right? So, and increasing on that is kind of difficult. So you have to find some other, and machine learning methods are not built for such lopsided training data. So not only that, but we actually had a lot of iterations where we would sit there looking at tables, and we would say, is this a good table, a bad table? And we realized that a lot of the time we just didn't agree. Okay, what does it mean to be a good table? Is it, is there some absolute notion of good table? Is it, well, to me it's about coffee. Is it interesting? Of course, but if it's about, some other personal ranking of some books, maybe not. I'll show you examples in a moment. And so it turns out to be very application dependent. So here are examples of stuff that you can easily prune out. So a lot of the HTML tables on the web are these layout tables. Why? Because HTML just doesn't have a different way of putting things in rows and columns to make them look beautiful. So they harass HTML tables. And you'd think, there's a schema row, right? There's a way of creating a header row in HTML, so you can actually make it clear that maybe this is a header if there's other stuff. Well, nobody uses that. Okay? And they do it also for layout purposes. This is an example of utility is kind of questionable. So what is this? This is my top 10 John Holt of Washington. I don't know what this is. This might be interesting to me or to the creator, maybe to some of his friends, if he's Mohan with 5,000 friends on Facebook. Yeah, that's a reasonable thing to do. But those things are rare. So some of these facts are very obscure or very personal interest. Vertical tables. These are about 15% of the tables on the web. They're vertical in the sense that they're about a single entity. Okay, so they don't follow any of the normal forms that we love. They take all the attributes, they put them in the first column, and the values are in the second column. Okay, so they're actually interesting tables. They have very valuable data, but they're not multi-entity tables the way we're used to, at least in the database world. We actually show these in search results today when they're relevant. But you have to change your techniques in order to deal with these kinds of tables. So what did we do? We had a bunch of structural features that looked at how many cells are full, how many is there a schema row, is there not, But what I think is the most interesting thing, and this is a lesson that I've learned again and again over the last few years, is try to find semantic signals. If there is some semantic signal in the table, that is a very high quality clue that this is a good table. So what is a semantic signal? Well, first of all, a header row. Header rows exist in, I want to say, 70% of the time, maybe overshooting there. The first actually feature we looked at is the subject column. So if there's a column near the left of the table that is about a bunch of entities, okay, that is good evidence that this table actually has, it's talking about a set of entities, and the other columns are going to be properties of these entities. Okay, so we developed a classifier for looking for the subject column, which annoyingly is not always the leftmost column, not just because there's a lot of content in Hebrew, it's because sometimes the leftmost column is like just a number, and then the second column is the thing. Okay, so not a huge problem, but when you try and get something done fast, you have to take that into consideration. And then, can you take those values and actually map them to a known database, the knowledge graph? So a lot of these data tables are going to be about properties of locations. Fine, these locations are in the Google Knowledge Graph. If you can map them to the Google Knowledge Graph, then not only do you know that this is, in some sense, this data is grounded in a database, but you can actually find the class of entities that this table is about. Okay, so you might be able to find out that it's about cities or about countries or about coffee-producing countries, something like that. Okay, and of course, the other thing is to try to map the table headers to properties in the knowledge graph, to the binary relations that the knowledge graph knows about. Now, the knowledge graph is very poor, relatively speaking, in the binary relations that it recognizes. But if you can map some of them, then you have more hope of understanding what the semantics of these tables here, and even the fact that it has semantics. So it's not a layout table, it's not a random collection of rows and columns. Okay. So we just let's skip over this. Right, so what we try to do is we take the values in the table, say we have these beautiful strings, we map them to entities in the knowledge graph. So obviously Georgia, the typical Georgia problem, we can map it to the state, we can map it to the country. And then we aggregate, right? We look and see that most of these actually map to a state. Some of them map to a city, some of them map to a country. But since the majority of them map to a state, we're going to say, well, this table is talking about states, and so we rule out the mappings from Georgia to the country or from New York to the city. Okay? A lot of the time that works, but some people on the web author stuff where you'll have a bunch of countries and then you'll have a city in there, or you'll have something else. So people, for some reason on the web, when they author HTML tables, they did not read any database textbook. Okay? And they just do whatever they want, and you got to deal with it. Okay. So how did we deal with the fact that no classification will work when your data is lopsided? So first of all, we wrote a bunch of rules that removed 90% of the bad tables, calendars and stuff like that. So now you only have 90%, which is bad stuff. Okay. So then we wrote another classifier that was focused on high recall, so not to lose content, but threw out a bunch of other bad tables. And so now we reached about 50% precision, and then we had a fancier classifier that actually looked at a much more balanced training set with positive examples and negative examples.
Forward. Just keep going. You still have time.
Just keep going.
And you can the details of the machine learning are, they are interesting, but not the focus of this. So, but the bottom line was, we got after we have the power source fixed, we have about 83% precision on horizontal tables, in other words, tables that are about multiple entities, and 89% precision on tables that are vertical tables, in other words, they're about a single entity and the properties of that table, of that entity. And that was sort of that is our basic corpus. which then we filtered even more in specific applications. Thank you. Okay, so what did we do with this corpus? So the first thing we did was we implemented our dream, which is a search engine for data. Okay, so we implemented table search, which is based on the Google serving infrastructure, except that we, in addition to the typical Google ranking, we also added a bunch of signals that that matched against the subject columns in the tables, and if there was something in the query that actually matched a value in a subject column, that got ranked pretty high. So this is what it. So you can actually go to research.google.com/tables. Here is a picture. You can surprise. You can search for countries by coffee production and see what are the top. This is the example that drove most of the research. Yeah.
So how many of these tables came from Wikipedia?
A large chunk, but not 99%. So.
What's the proportion of good tables in Wikipedia as opposed to
It's higher, but also in Wikipedia you have a lot of stuff that is layout, and the layout there it looks even better because it does have a little bit of structure. It's some navigational tables that actually point you to other places. So actually finding the good, only the good tables in Wikipedia is actually a tricky problem. I think there have been some conversations with the Wikipedia Foundation to actually create a different HTML for the good tables so they can be understood better. But I don't remember what the number is for how many of the tables can compute. But it's not like that you can just ignore everything else, and I mean that would reduce your recall by at least 50%.
To figure out if you trust the table, do you look at the content at all and the redundancy? I'm assuming there's a lot of redundancy between tables.
Yes.
Right? Do you look at those values to see if they're
No.
consistent? Or?
So we do trust the web way. In other words, you look at the URL and decide whether, and you could imagine looking at multiple tables and see which values there is agreement on and stuff like that. We didn't go
Just
there.
kind of
Yeah.
pop up the trust in the table.
So there's a problem with that, which is, so you could do that, but when Google starts aggregating values from multiple websites, we get into legal trouble. Because now we're adding value over individual sites, and then you have to start talking to lawyers, and then you have a fundamental question: am I going to live my life, or am I going to talk to lawyers? I don't know about you guys, but mine. Peter.
So in your earlier example, you were talking about trying to figure out if something's talking about states, and you said, well, if some large percentage of the entities seem to be referring to states, then we'll say yeah. So are those sort of magic constants, particularly in your handcrafted rules, or are there sort of more, say, principled ways of that?
Principle. Let's do the principle one. Yes. So what we do is we try. So states is a class is a category in Freebase. So and Freebase has thousands of categories. So we try to find, is there a category, or it's called types there. Is there a type in Freebase that is a concise representation of the values in this column? So if somebody tomorrow adds another type to Freebase, we would recognize that too. Now Freebase types are kind of very they're not very detailed. Okay, so for example, you don't have coffee producing countries in Freebase, but you can go on the web and you can find, using Hearst patterns, you can identify things like the class of coffee-producing countries, with the 44 countries that produce coffee, and you can conceivably have that as a much more rich set of concepts to match to. The problem with those techniques is they also give you a lot of noisy data, and so you end up. Initially, we did it with respect to categories found by Hearst patterns, but when we went to production, we went to knowledge Freebase categories.
Going back to the Wikipedia boundary discussion, isn't it also the case that in the case of especially people pages and so on, it'll be one of these single entity kind of tables, right?
Yeah.
The knowledge graph kind of thing that they have on the right side. Is actually talking about.
Yes. And we actually, the single entity tables are actually you use it in a very different way, actually, in search results too. But so yeah, so the whole question of trust and of this data is it's in the eyes of the searcher. Okay. So that's what we have for table search, and we have a bunch of nice features here, like you can export this into Fusion tables or into Google spreadsheets. What else? There are some data-friendly snippets, stuff like that. But that's data search. That's for people like us who like to search for data, or researchers who are looking for data in a constant, more focused way. Another application of
Well, actually,
So the context for a table comes, so list of coffee production, that's time dependent. How does the user know that that's coffee production this year or 10 years ago or whatever?
That's a really hard problem. So, and in fact, this is one of the
Oh, well, related question, normalization of values. So say I saw pounds, kilograms, 60,
Right.
60-pound bags or whatever. So how do you normalize across?
So that would happen later. So I said, the way to think about what we're doing is we're doing search and discovery. Any value that you want to get, any value or use that you want to get out of the data, you need to do that. So now if you have an application or you need some analysis that is done in kilos and not in pounds, and the column is not in the unit that you want, you're going to have to do that in the application that is going to manage your data. What we're doing is we're finding the data in some form for you that you can start working with. Right? Now the year, so right, we actually have, there are pages for coffee production in every single year, and all these pages look alike, except there's only one token on the page, which is not terribly prominent, which is the year of that data. We haven't solved that problem, okay? That's hopefully, the hope is that the web ranking will take care of that to some extent. So the page about the coffee production in 2006 will not be ranked within Google, just as a document, as high as the coffee production in 2015. That's a signal that we can get from other places.
Does Google search only HTML or how about FTP, for example?
It'll search anything that it can bring into its index. So
PDF?
it has PDF files in it.
Do you extract tables out of PDF?
There are people working on extracting PDF files out of tables out of PDF. There is a lot of, and PDF changes the problem a little bit, right? Because in PDF you can actually find, especially if you're looking at scientific papers, there's the caption, right? The caption is referenced somewhere else in the paper, and maybe the text around where that reference is can actually help you understand the contents of the paper. We did some work on lists. Lists are poor man's table, right? People who don't know about cells, they don't know about rows.
Can you talk a bit more about figuring out how relevant the table is to the query itself? I don't know if it...
Yeah, it's coming, but let me talk about it now. Now we have to do it. So we look at the query, okay, and I'm trying to think about what I can say without getting fired. Okay. I've been there a decade. It's about time, anyway. So let's say this, okay? So, and I'm talking about on Google.com itself, okay? Not in table search, even though it's sort of similar. So when you look at Google, when a query comes into Google.com, it'll produce a ranking of documents. Okay? We don't touch that. We don't want to get in trouble there. Okay? Within those documents, we will look in those documents to see whether there is a table that is known to our table corpus that might be relevant. So that already gives us a huge lower bound on the quality of the table and the relevance of the query. Okay? So we already rely on the search engine that does this a few billion times a day to rank documents. We rely on them to give us a bunch of candidates. Then we have our corpus. We check in our corpus to see whether this document contains a table that we have determined to be high quality in our corpus. And now we look at matching. So now we say, okay, are there tokens in the query that we can actually match to particular rows in the table? Okay, you'll see this in a moment. Because what we're trying to do is we're trying to also give you not only the table, we're trying to give you a few rows of that table because we have limited real estate on top of the search result table. Okay, so we need to select rows. We may even have to select columns because some of these tables are really wide. And when you're putting things on a phone, you need to select 3 or 4 columns that you're going to show the user. So we're trying to see, is there a match to particular rows, to particular schema, and to any very prominent words on the page that we deem to be very descriptive of this table.
And the type of elements inside the table.
Yeah, so the idea would
It's
be...
a number and it's a numerical question.
That's a good idea. We don't actually do that yet. They do that in other contexts. Actually, I don't know. Maybe we do. There we go. Okay, so here's another application that we didn't anticipate for our tables, which is Google Docs. So in Google Docs, there's a research tool where if you're a high school student and you're writing an article about Abraham Lincoln, you can now be super lazy and go into the search tool here and say, give me an image of Abraham Lincoln, and drag that into your document. You already look profound, right? And you continue writing your stuff. Go get to Wikipedia, a little bit more text. So now we added to this table search. Okay, so now if you really want to look smart, you want to put data in your documents, and you can go and do table search. And this is Islam in India. You can find tables, and then you can. Now we're back to coffee. Okay, list. We're back to coffee. List of coffees by countries by coffee production, and you can basically select some of the rows and drag them into the document, and voila, you look smart. So this is actually one of the most popular features in the Google Docs research tool. But the holy grail at Google is to get into the search result page of Google.com. And so finally we decided we're going to go for that. We found the right connection with the right people, and we decided to invest our lives in this. Okay, I'll talk about the. I should say this is work done by a lot of people. They will be mentioned very soon. Okay. So this is critical temperature of krypton. You see what we did here is we actually found the table, which was in one of the top results, but we selected a row from that table and put it on top of the search result. Okay, and this is really important for, especially on mobile. I was having a conversation 2 weeks ago with somebody who's working on fiber in Uganda, and I asked him, what is the percent of literacy in Uganda? Who actually cares about being connected to the internet? And I just asked my phone, using voice recognition, I didn't have nothing to do with that, and came back pop saying the number which I now forgot. That's a little bit small. So, but it gave me the answer right there, and it was very useful from the table. So here again, we try to find and see here that you have to select very specific columns for the answer. You have a query and you might have 10 columns. You can't put 10 columns on the top of the search results, not even on a desktop, let alone on a phone. Okay? And actually finding those right columns turns out to be one of the critical problems that reduces our coverage. Okay? So now I can go on and on, all kinds of interesting tables, like all-time top scorers in Europe, all kinds of good stuff.
These tables, the website change like every day, so how we can...
We will give you the table that we found today. So we crawl every, I don't know what the frequency is, it's pretty frequent, but we will give you just like the way you, so this is no different than crawling pages on the web. It's folded into them. And I can go on and on all day with good examples. The state of entering the union, poker, probability of royal flushing poker, that's exciting. And this is the answer that enables me to retire. now when you come and ask for top coffee exporters, you actually get this from Wikipedia, and I'm kind of close the loop, as they say. Yeah.
So, if you find two tables that contain similar information, how do you disambiguate them? Or find out which one is the one that you want to show based on conflicting information that you may find in two different tables?
So we're not going to go and look at whether they're conflicting or not. So
Okay.
the question is a good one. Like, right? If you could say if they're the same, it doesn't really matter. If they're conflicting, we need to make a decision.
Right.
So we don't actually go to that level of analysis, say, are they the same or not? We're not actually, and most of the time we don't actually understand the table well enough to actually know that that they are in agreement or conflicting. So I have to apologize to all the people who think we did some very deep schema integration, just because the person who's standing in front of you. No. Okay, so this is we have a guess. We think that there is a column in this table that answers your query. We don't actually have that mapping spelled out anywhere, so we don't know for sure. We cannot compare a table on this page and a table on that page, certainly not at query time, and make a judgment that they're the same or conflicting. So to answer your question, we'll probably pick the one that's ranked higher by Google, or that we were able to extract the relevant row with more confidence.
How small did your search time read get onto that front page on Google search?
Very short. There for every service at Google, when a query comes in, right, it goes into a bunch of engines, and they all vote for different possibilities. I understand weather, I understand flights, I understand tables, and all of these have to come back very quickly. I don't actually know what the number is today, but so we have to work under these constraints, and a lot of the engineering that went into this is making sure that we do that. A lot of engineering took into consideration that the crawling of tables is done with the crawling of pages, so we don't add extra. We don't have a corpus on the side like we used to do in the beginning that you have to go to in order to see whether it's in the table corpus. So all the annotation of tables now happens as part of the Google crawl and indexing, and that's a lot of heavy lifting, which the names of the people who did it will be on the next slide.
So just for the heck of it, I just did a search on big data revenue to vendors, and so up popped a table. The first column is vendor, and then the other columns are big data revenue by absolute percentage and so on. So for some reason or other in my search results, it stripped off the first column of the vendors, and there's this sort of vertical thing which says vendor, and then like 3 vendor names. A row sort of above the table. Now, if you export it, you see the full column. I'm just wondering, is that a feature?
Send this to me later. I'll look at it.
Oh, okay.
Is this in Google.com or in table search?
This was in table search. Yeah, I'm just wondering whether you somehow say that certain columns are header columns or...
Yeah. So actually, header columns are hard to identify. Sometimes you have multiple header columns, but you might have especially if somebody is trying to emulate a spreadsheet, then you'll have crazy things going on. Yeah.
So you said this is using the knowledge graph to kind of determine what the column types are or the quality of the column type. Are you feeding the knowledge graph with what you're learning from tables?
We would like to. We had many discussions about doing that. We don't. And there are multiple reasons. One is making sure the quality is high enough. The other reason is in order to take data, and I think I'm quoting the words correctly, okay? Data is considered public if it appears in 3 independent sources on the web. Okay, so if you're gonna look for coffee producers, there's actually only one reliable source of data on the web that tells you how much coffee was produced by different countries in the world. Okay? It's the International Coffee Organization. Everybody else copies from them. Okay? So we cannot actually claim that data to be publicly available and therefore put it in the knowledge graph. There are other ways of getting to that data and attributing and doing stuff, but that's not part of the knowledge graph. If you search for, I hesitate to try to go to a browser, but if you search for World Barista Championship, say 2014, okay, you will see, I hope, today, information that was supported especially by somebody at Google who knows something about World Heuristic Championships. Okay, and that's fed into a separate pipeline. So somebody decided that okay, it's me. I'm authorized to take the 16 tuples of World Heuristic Championships and put them in a fusion table. And here are a bunch of queries that will match against this content. And now it's served on Google.com. But that's different than putting it in the knowledge graph. Data gets complicated when you're trying to make it available to everybody. We can stay on this slide for.
No, it's okay. We want to do this. Try that.
Okay, so these names should have appeared a long time ago, but now there's context. So as I said, the people on the top, they started the project as an intern project in 2007. Okay, for those of you who remember Sigmod in Beijing. Okay, that's when it started. Petros, Marius, and Saint-Chi, they did some of the semantic analysis of tables. You actually made Google search happen, so he came to Google and decided this is really nice, but let's make it real. So he recruited a bunch of people, including Afshin, who's a top machine learning guy, to actually make the table corpus. And then when we decided to go for the real thing for Google.com search, Jane Madhavan, Halevy, and Sri Balakrishnan, and Warren, who's actually my academic grandchild, which is sad to say, sad for me. They actually went, so this is actually interesting. Once we got approval that this is going to happen on Google.com, they actually transferred from my team in research into the search team and made it happen. So this is an example of where technology transfer happens by donating people. In this case, it worked really well for the individuals involved. So that's what we did. Okay, so that's it for web tables. But here's the problem. Okay, so web tables, so here's a table, right, on the web. And so the basic problem with web tables is we can increase our coverage much more if we actually understood the semantics of the table, right? If we could actually understand that this table is talking about something that this person is asking about. But this table is a beautiful table, it even has a header row, okay? But unless you're me, and maybe you've already been looking carefully at the data on this talk, you don't know that this is data about coffee-producing countries, because it just says kilos and 60-kilogram bags and stuff like that. Even though, and in this case, there's a title saying, list of coffees by coffee production. But still, that text might be pretty long, right? There's going to be a lot of text around the table. And how do you know which tokens in the text talk about what this table is really about? So the idea of Wikipedia was to say, well, suppose we knew all the attributes that countries could have. They could have GDP, and they could have capital, and they could have coffee production, they could have quinoa production, they could have, fire hazards, cheese, and stuff like that. All these things. Okay, if we knew all the attributes that countries could have, then we could look at the text and say, well, coffee production, yeah, we know that that's an attribute of countries, and it's very prominent, and there's other evidence that can convince us that this is the table about coffee production. Okay, and coffee production, just to make it to be very humble about it, when you look at the attributes that countries have, it's ranked below 4,000. Okay? That's sad. That just tells you that countries have a lot of stuff. It takes them 4,000 attributes to get to the really important stuff. So the other motivation for Wikipedia was that we're extending the knowledge graph all the time. So somebody gets up in the morning at Google and says, this quarter we're going to do red wines. People are interested in red wines. We're going to start investing in the knowledge graph, and obviously it's already done. We're going to invest in red wines. But how do we know what people care about with respect to red wines? So wouldn't it be nice to know what attributes of red wines people care about and query more frequently? And the bigger question is, the knowledge graph is, I'm sorry to say, it's a database. It's not a knowledge graph. The knowledge graph goes to marketing. It's not much better when you can tell it, right? But it's a database. And the schema of the knowledge graph is basically the attributes for which there is data. And when you go to the knowledge graph schema team and you tell them, you should really have coffee production in your schema, they don't. Okay? And they say, well, we're not going to put it in unless you give us reliable data that we can put in the knowledge graph. And the answer is no. we should know about the properties of objects in the world regardless of whether we have them today in the knowledge graph or not. Because that will enable us to understand queries much better and actually less frequently give wrong answers or lead users the wrong way. So this whole thing sort of started the conversation of, yeah, we have entities and we have a database, but should we actually really understand the schema of the world in a more flexible fashion? So Viberpedia is the attempt to start driving that discussion. So what we did was we decided, okay, we're going to just find all the attributes that exist that people care about. People care about means it's already either in the knowledge graph, or it's very prominent in the query stream, or people write about it a lot in text. Okay, so we have attributes, and it's going to be a dirty anthology. Okay, so it's not going to be something that's beautifully curated as a knowledge graph. And so I'll tell you how we built it in a moment, but it's right now it's 4 to the magnitude bigger than the schema of the knowledge graph itself. And the thing that I found most important about Viberpedia is that it's a schema for search applications. So we're not starting and saying, oh, we need to model the world. We're starting by looking at stuff that appears in queries and text. We think these are attributes or properties, and lift them up. Start understanding them. Start understanding, oh, these things have a domain. Do these things have a range? Are these attributes related? Are these, is parent, is father related to parent? Stuff like that. So we're coming from the content and trying to recover as much of the semantics as possible. Okay, that's the approach that we're taking. How did we do this? So we first of all assume that the classes in the world are given. So we know about countries, we know about U.S. presidents, red wines, what have you. Okay, this is in the knowledge graph. We've got these entities. Let's declare that problem done for now. So then we go to our unfair advantage, which is the query stream. Okay, we look at queries that have the form. What is the X of what? What is the GDP of India? What is the coffee production of Brazil? Okay, there aren't that many queries like that compared to the total number of queries, but those queries are very high precision patterns that can give us these X's. Okay, so now we know that population is linguistically it's been used a lot as a property. Fine. So now we can go back to the query stream with all these X's and look at other queries that just give you entity and property. So we know that population is a property, but now let's look at what is it a property of. Okay, so now we go and we find many more queries that give us that population is associated with Norway, Sweden, Iceland, Israel, India, and now we can start doing counting. Okay, and so we can see that, for example, that population is associated with 422 instances of countries. Now you might be looking at it like, last time I checked, there were 422 countries in this world. Okay, well, the knowledge graph has a lot of historical countries, okay, that don't exist anymore. And actually, people ask a lot about the population. But population also applies to cities. It also applies to biological species. So it applies to all kinds of things. And Viberpedia will collect all of those. So this is.
Are you paying any attention to the semantics at all? Like, if there were to be some synonym for population?
We'll do that in a moment. Yeah. We'll get there. So this is getting it out of the query stream. And obviously we have filters, so we only look at things that appear a certain number of times, stuff like that. And sadly, after doing all this, I actually wrote the code. And this is the happiest time in my decade at Google I sat and I wrote code. This is a job to be improved, like the happiest person around. Probably because I just finished writing the data integration book and I didn't want to think about it anymore. But so I look at the results and I don't see coffee production. I think somebody set me up for a really bad midlife crisis or third midlife crisis. So then what we do, and the reason is irrelevant. So then what we do is we go to text. Okay, so we got a lot of attributes out of the query stream, but now we can use those as examples to go to text. So we take the top attributes that we found from the query stream. We assume those are high quality. So for example, GDP, and we look at patterns in text that mention GDP with the entities that we know that they apply to. So we find a sentence like the GDP of X rose by Z. Great. That's a pattern that somebody is talking about GDP. So now let's take that GDP and see what other terms appear in the same patterns, but not about GDP, about something else. voila, we got coffee production. Okay, so coffee production came in, and now again I can retire. So now we have this huge collection of attributes, and we group them. So now,
So you're saying you do care about attributes that nobody's really querying about?
so they don't query about them as often as they query about GDP. But if you actually look at the absolute number of queries about coffee production, it's pretty high. So the tail is, that's in web search, right? The tail is long and heavy. The other reason to care about it is that if you understand, even if you know that this is an attribute and you don't have the data for it, then you can analyze documents a little better. You can actually identify that there's a web page with a table there. It's okay to know what you don't know. And the knowledge graph is always going to be a small fraction of what people have to know. So now we look at synonyms. Okay. So now again, we have all these surface forms of attributes, and now we start looking for synonyms. So and synonyms are difficult, right? So if you have sorry, let's talk about misspellings. So most people, first of all, 15% of attributes that we had in Wikipedia in the beginning were misspelling because people type badly on their phones. Okay, and those are tricky because motor can be mother if you're talking about people, or it could be motor if you're talking about cars. So it's very dependent on the domain of the attribute. So we use, again, and here we rely on existing Google infrastructure, which is the spell correction. So we look at those strings. If they correct the same thing, we're happy. Same thing with synonyms, and that's so we try to see whether the synonym detector in Google actually corrects the same or find the synonym, and then we do that. It's not high recall at all. There's much more work to be done there. And we try to find super and sub attributes in order to cluster them. Okay. Okay.
Murphy's law.
So, just to close out here, I want to make 2 points. One is, first of all, we have a large ontology. Okay, so if you compare, so the number of unique attributes is 67,000. But if you actually look at the pairs of class and attribute, then you're millions. 11% of these are in Freebase, in the top, even in the top 500. 6% only in the Wikipedia. So we're really extending existing ontologies by quite a bit, but we're adding a bunch of them. Okay, so at 5,000 attributes, we're at 52% precision, meaning half of them are actually good attributes. We've actually improved this since then. There's a way to go. And since I want to save some time, we went back to the HTML tables, and we found when can we actually look at tables and see here are attributes either in the text or in the header row and map them to Wikipedia versus to the Google Knowledge Graph. And I'll jump to the result here. We found almost 6 times as many more possible mappings to Wikipedia than to Freebase itself. Even on Wikipedia tables, there are a factor of 4 more mappings. And even for tables with no schema, so you have no hope, okay, to do any, we still were able to find 22 times more mappings from the text around the table to Wikipedia than to Freebase itself. So there's a lot of, and this is not surprising because the content in web tables is the long tail and the knowledge graph is not. So there's another opportunity here is now that we have an interesting, a really large set of attributes, we can start mining structure in that set of attributes that can reveal interesting things, but I don't want to talk about that yet because I'm trying to save some time. So, a few observations from Wikipedia. We find good attributes for a lot of classes, but they have to be famous. Okay, US presidents, countries, stuff like that. We don't find attributes for spoons because nobody goes on the web and says, well, the famous spoon, blah, 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 has a length and a width, and I don't know what else we have. It's because the way people refer to spoons, they refer to them as nominal objects, not as objects with names. So if objects have names, we will find attributes for them. For spoons, you're going to have to develop other linguistic techniques to find spoons. It's not actually that hard, but Wikipedia doesn't do that. there are a lot of good attributes in the tail. So even if you look for countries, we have over 100,000 attributes, and if you look around 100,000, you will still find good attributes. Okay, like firearms experts of a country. It's around 100,000. Okay. And the best thing about Wikipedia is it's a launching pad for a lot of really interesting discussions. So if you look at some of the top attributes of Wikipedia that people ask much more often, they're things like the economy of a country, culture of a country, the legacy of a president. Now that cannot be encoded in the knowledge graph as a triple, or even a set of triples. But this is information that represents stuff that people are really interested in. And as a search engine, I think we need to think of ways to answer them. So maybe we can't answer it in one sentence, but we should be able to cut that, take culture and break it down to a bunch of simpler properties and say, well, the culture of this country is a bunch of artists, a bunch of painters, or musicians, what have you. Okay, so the last part of my talk, which I'll do very briefly, is mining subjective properties. And did I mention the people? Stephen Wang. Where was that? Stephen Wang is the main guy on Wikipedia. Emmanuel Trumer, it seems that PFL is the main guy who came up with this idea, and he was an intern at Google last summer. Sunita and Rahul Gupta were on this. So remember, I started out by saying that the knowledge graph is only objective facts. Okay? But a lot of queries are actually asking about things that are kind of subjective. So if you're looking for cute animals, okay, the knowledge graph won't have cute animals because we can't defend it in court. But if you look at the web, there are animals that are cute, there are animals that are not cute, and there's pretty widespread agreement about what those are. Okay, big cities is another example. It's slightly more challenging because it can be very relative to something. But people ask that, and we already know that. Sorry, I had to put this example somewhere in the talk. We already know that Google looks for answers from web results, but and that's what we're going to have to do for subjective answers. So this is why is the sky blue? Now we know why the sky is blue. Google told you why. Okay, so we're going to follow the same kind of methodology, which is to try to find from the web search results or from the content on the web an answer that we can stand behind. Okay. So the thing is here, when somebody asks you about cute animals, you can't just go to one website and you get the list of all the cute animals, the non-cute animals, and you're done. You're going to have to go to a lot of sites and aggregate the results of the sentiments that you find there. So approach number one would be, let's just extract from a whole bunch of sites and then count, okay, and see a majority vote. So Emmanuel did this experiment when he started his internship, and let me explain this result. So here we did it on something where we could actually measure the results. We looked for big cities. We looked at cities in California. Okay, we said how many let's extract all the cities in California, how many of them are said to be big, okay, with some number of time, okay, or those claim to be not big. And this is the population. So the population is some proxy for whether the city is big or not. And what you can see by this very confused graph is that the majority vote doesn't actually tell you anything. So there's no correlation between whether the city is big to the population. I mean, the not-big cities have pretty much the same distribution of number of populations. So counting and voting doesn't work. And the reason for this is that there is a bias. People write more about big cities. They don't write as much about smaller cities. And this bias depends on the actual property that you're trying to mine. So what Emmanuel did was he developed a probabilistic model. Probabilistic model said, okay, let's assume there's a dominant opinion about whether a city is big or not. Okay, and there can be many people that either agree or disagree with this dominant opinion. But so you have multiple users. Users are authors of content on the web, right? And so there's a probability that if there's a dominant opinion, then what is the probability that user number one or user number two will actually hold that opinion? Okay, holding that opinion is step number one, and then there's a probability that the person will actually express that opinion. Okay, so people express certain opinions about big cities in different ways that they express about safe cities or about good animals. Okay, so now you have a probability baseband here that tells you, it starts from where you can count the number of statements that you see on the web of whether a city is big or small, or whether an animal is cute or not. Okay, and you can infer from that, if you can actually find all the weights in this graph, which you did using an EM algorithm, you you can infer what with some degree of confidence, what is the dominant opinion. And I'll jump to the punchline here. This is what he gets from this probabilistic model. So after taking all this probabilistic model into account, the cities that were predicted to be big really had populations that were much bigger than the cities that were predicted to be small. Whereas here, this is the count and majority vote. So it really depends on the particular property that you're trying to mine on the web. And this is interesting. So I think this is from so we compared this to, just one second. Yeah, okay.
The question is about the previous slide, how do I keep this? So you said that big cities get written about more than small cities. So if you try to do the same thing for cities that are small versus cities that are not small, does it work as well?
So we're looking at the entire corpus and all the cities. So it is true that if you actually removed a bunch of big cities, then your probabilistic model might zoom in on the smaller cities, and you will get higher fidelity there. He didn't do that experiment. That's an interesting question. Big cities is I hate this example because what's that? A small city in China is bigger than Tel Aviv, right? So it's like.
Well, that's what makes this problem hard, right? Is that big is relative to the actual context that you're in. And so, in this case, it looks like you would say with your probabilistic model that some city is always big, but that's of course, if you're asking if the query is about cities, big cities in California, actually having the context in California makes the problem very different than just big cities in the United States.
Right. And I think you can actually fix for that. But when you talk about cute animals, so I know the example of big cities actually leans more to the future research than to this. But on there are other properties that are more in agreement and less a matter. Now you can say, in China, geese are really cute. Okay, they're not in the United States. There's always that. And so you can imagine, looking at only content in Chinese or stuff like that. But that's, as we say, future work. Okay, so let me conclude. So first of all, I want to make it very clear: structured data and web search results is a huge deal. The number of engineers working on various forms of structured data is in the hundreds. Okay, it's a large org. Okay, in the search org. Okay, it's a big and complicated, and you think everything gets. When I showed you the property queries like Mike Stonebreaker Awards, that comes from one team. Right? Woody Allen movies comes from a completely different team. If you ask for quarterbacks of NFL teams, that's going to come from a completely different team. So it's interesting to see how structured data can be broken up into so many teams and possibly not the most optimal way. But then, what is coming next? Most of the work is on stretching the head. Okay, so we're looking at the query stream. We're looking at where we can answer more queries that are clearly significant in the query stream and extend the knowledge graph. Not only to more content, but also to more languages, which is really critical for the overall happiness of our users. As I already said, there are more complicated queries, like the culture of the country, or the economy of the country. I think we should be doing much more there. Today we just spend it with the media, which might be okay, but I think you can actually do more if you want to get a quick sort of overview. Putting answers in context. So for example, you can ask about the origins of Hebrew. Well, yeah, I can give you the origins of Hebrew, but I would like to know what other languages were developing in the same time in the world. Right? It's a much more interesting answer than just saying, the origin of Hebrew is Aramaic. Yeah, okay. Or the evolution of money. That's another. These questions actually came to me by reading a great book that I recommend to everybody. It's called *Sapiens* by Yuval Harari, who explains the history of humanity from the beginning until now. It's a fascinating book. It's translated into English finally, and it's actually hit the big time. So I read this book, and I came up with all these. He gives a lot of facts in here that are fascinating, and I knew that I would promptly forget once I finished reading the book. And my reaction was, well, Google should be able to answer these for me when I forget, and we can't do it. Okay? I'll end here. There's a lot more to do with structured data and search results. Yeah.
So does Google Lens also search for answers in PDFs? Or is that?
There have been several efforts on that. Yes, but I don't know what the status is. So, whether it's close to production or not.
So some things you can do legally, but other things you can't do legally. I didn't quite understand. So you can do these aggregate answers, and that's all fine to figure out what animals are cute. But there were certain other things that you could not do because the lawyers would yell at you. How does that work?
So the simple answer is I can publish anything in Sigma. Okay, so yeah, I can aggregate cute animals and publish it in Sigma. This was not in production. This is a very exploratory project. I don't know. We haven't asked the lawyers about actually aggregating from like 10,000 sites and seeing something. You could imagine. I mean, you see today things where you have an answer and you're saying this answer is according to this particular site. If you actually give attribution right there, it's okay. Now for cute animals, if you've aggregated this from 10,000 sites, what are you going to do? Give attribution to one? The UI people and the lawyers can get together and figure this out, right?
But the issue is more kind of using somebody's content without attribution.
Right. Okay. So last time we talked to those particular lawyers, if you have a fact that appears in 3 different sources on the web, independent sources, it's considered fair game public knowledge. So now you can go and put it in a knowledge graph that you serve to others.
Even if they all say Wikipedia says this, they're independent sources. Never mind.
No,
Okay.
that's a good point.
Okay.
And so you have to make sure that's not happening. Sometimes people copy from Wikipedia and they make changes.
So many times when one is doing a search on Google, one has to also think about, what are the pure keywords that I want to search for, where in general our past experience says, hey, the results would be good. Whereas where you are trying to get to is no matter how I search it, the results would be good in the sense that, I'm asking about culture of some place. I could just say culture China 1650 or something. Whereas, so now the question is that in terms of searches in the future, will there be a time where I could literally have just a true conversation with the search engine about, accent search? That's a topic that I don't know about.
We're certainly working on more conversational interfaces. And I think that today, especially on mobile, right? If you ask, I don't know which of these are in production, but if you ask, restaurants in Palo Alto, okay, so give you a list of restaurants, and then you say only Chinese ones. So the conversational interface will understand that only Chinese ones is a restriction in the context of the conversation. So we're certainly trying to enable sessions where the context is continued or saved essentially. But this is driven mostly by mobile. Sure. But I mean, the Google search engine always tries to make it such that it doesn't matter which words you use, you'll get the right thing. But there's so many different techniques to come to bear on that.
So the more general version of this would be relationship to WhatsApp analysis.
I should turn the question back to you guys. So I think the Google Knowledge Graph is trying to cover more information about the world in general, not going into particular domains in any specific depth. And I would say that the inference that we're doing over the knowledge graph is I wouldn't even call it inference, right? It's lookup. Now lookup is hard because lookup is sometimes you have to look at what the words in the query and figure out that this is how it maps to a real an explicit fact in the knowledge graph. So that's not inference. That's just understanding the query. Right? Doing a join, understanding that you're looking for anything that requires doing a join between two things. We don't even that simple inference. We don't do that. Okay, we have the biggest AI lab in the world. It will happen. And we're doing deep learning together.
Thank you, Alon.